everyone, and thanks for coming to my talk about the Java module system. I give this talk today because 1.5 years ago I needed to modularize a software framework. I work for Scoop Software, and we have an open source framework called Kapselung, which is a workflow engine that allows you to describe your workflows in pure Java. This framework was Java 8 compatible, and my job was to make it compatible with newer Java releases and to modularize it. At the same time, we wanted that it still worked with Java 8, which doesn't know about the Java module system. I had some challenges along the way, and I want to talk about them today. I was also surprised that I needed a significant amount of work in order to adjust our build process to the Java module system. And that's why I became interested in how to make the build process easier. And since then, I contributed to several Gradle plugins for the Java module system, and I also created a few plugins of my own. My goal today is to show you that things changed a lot in the last year or so. And these days, you can build your modular code with minimal effort using tools such as Gradle or Maven. We will look at typical use cases, at things you usually want to do with your modular code, and I'll show you how to automate these things with Gradle or Maven. But before this, let's talk a bit about the Java module system. Since Java 9, the JDK is no longer monolith. It has been split into several modules, and here you can see the module graph of the Java 9 Standard Edition platform. At the top of this picture, there are several modules related to the Enterprise Edition. And because they don't really belong to the Standard Edition platform, they have been deprecated in Java 9, and they have been removed in Java 11. Now, having code removed from the JDK means that even if you don't modularize your software, even if you don't make any changes to your application, you may still have problems running it on Java 11 or newer versions. And to illustrate this, let's consider a small program that prints the XML representation of an object. I have here a product class with ID, name, and price, with accessor methods, getters and setters, and a toString method. Because I want to serialize this class as XML, I also put here the XML root element annotation. In the main method, we instantiate a new product, we marshal it, and then we print its XML representation to the standard output. For the sake of completeness, we also have a unit test class to test our product. There is not much to test on this class, so here I only check if the toString method works as expected. And we build everything with Gradle. This is our Gradle build script, and here in the dependencies block, we only need to specify the JUnit test dependencies. So let's try to execute this code, first using Java 8. So I will say Gradle run, and as expected, it printed the XML representation of our product. Now let's try to do the same with Java 11. This time it didn't work, and the error message says package JavaX XML bind annotation does not exist. This happens because the JavaX XML bind annotation package is part of the Java XML bind module, which has been removed in Java 11. The code removed from the JDK is still available in public repositories, such as Maven Central or JCenter. And here I compiled a list with the replacements for the removed modules. In our case, we missed the Java XML bind modules, so we need to use this library instead, which means that in our Gradle build script, we need to add this line. So let's do this. I'll put this line in our Gradle build script, and now let's try to execute again our code with Java 11. And this time it worked. So you see that we had problems running our code on Java 11 before even starting to modularize it. But we want to modularize our code. And to do this, we need to add a module descriptor to our application. A module descriptor contains metadata, such as the module name, the module dependencies, the packages exposed by our module, and so on. We put all this information in a file named moduleinfo.java, which gets compiled to moduleinfo.class, and this is our module descriptor. So, moduleinfo.java contains information about the module dependencies, normal or transitive dependencies, about the packages exposed by our module to other modules, about the packages opened for deep reflection to other modules, the services used by our module, and the services provided by our module, and the implementing class. We see that the Java module system provides strong encapsulation. A module can specify which parts of it are visible to other modules and which parts of it should be hidden. But sometimes we may want to break this encapsulation. We may still need to have access to the hidden parts of a module. And we can do this because the Java-C and the Java tools provide us some options. For example, we can ask that a module should export a package that was otherwise hidden. We can ask that a module should read additional modules, or that a module should open an additional package for deep reflection to other modules. Before Java 9, we needed to put all artifacts in our dependency graph on the class path. Now we also have a module path, and this is where our modular code should reside, because modules are resolved from the module path. In order to configure our module path, we can use these options provided by the Java-C and the Java tools. So either module path or using -p. Now, depending on the type of an artifact, if it is modularized or non-modularized, and on its location, if it is on the class path or on the module path, we have 4 possible combinations. Before Java 9, we only had this combination, a non-modular artifact on the class path. Its modular counterpart is having a modular artifact on the module path. But there are 2 other possible combinations. First, having a modular artifact on the class path. What happens in this case? If we put a modular artifact on the class path, it is treated as non-modular, and it becomes part of the so-called unnamed module, which exports all code on the class path. It reads all other modules, but it is readable only from automatic modules. And what are these automatic modules? They have to do with this combination, having a non-modular artifact on the module path. When we put a non-modular artifact on the module path, it is turned into an automatic module, for which a module descriptor is generated on the fly. And this module descriptor requires transitive or other resolved modules. It exports all its packages, and it can read the unnamed module. So in a way, the automatic modules are a kind of bridge between the modular and the non-modular world, because they are the only modules capable of reading code from the class path, from the unnamed module. A package with the same name is not allowed to appear in 2 different modules. If we have such a case, we talk about split packages. And in order to deal with such situations, the Java-C and the Java tools provide us the patch module option. With this option, we ask that all classes from a list of artifacts should be merged into a given module. For example, with this command, I ask that all classes in the JSR 305 jar should be merged into the Java XML WS annotation module. Okay, now let's get back to our XML printer application, and let's try to modularize it. This means we need to add a module descriptor to it. We saw that our application requires the Java XML bind module, and additionally, we need to open its main package to Java XML bind. This is necessary because the code in the Java XML bind module uses reflection in order to analyze our classes and to generate the XML representation. Now, before trying to execute our modularized code, let's make a small addition. I want to see whether the code has been executed on the class path or on the module path. We saw that if we put a modular artifact on the class path, it is treated as non-modular, and it becomes part of the unnamed module. And in this case, this isNamed method will return false. Which means with this statement, we can check whether our code is executed as modular or as non-modular, on the module path or on the class path. We do the same for our unit test class in order to see whether the tests have been executed on the class path or on the module path. When I first tried to build a modular application, I thought that Gradle has first level support for the Java module system. So I thought that I don't need to make any changes to my build script. I quickly found out that this is not true, and I needed to make quite a lot of changes to my build script in order to make it work with the Java module system. Now, this is a thing of the past because last year a Gradle plugin has been created which provides full support for the Java module system, and we will use this plugin. But I think it's still interesting to see what you need to do if you don't use this plugin, because this will give you a better understanding of how the things work and what this plugin does for you. And my goal here is only to show the steps you need to take. I will not go into every detail of the code that will appear on the next slides. So, to start, let's try to execute our modularized application without making any changes to our Gradle build script. I will switch to the directory where I have the modularized variant of our XML printer program. So it's the same program, but we have the module descriptor here and this small addition to print whether the code has been executed on the class path or on the module path. And without any changes in the Gradle build script, let's try to execute this application. And it fails. And the error message says module not found, Java XML bind. This happens because by default, Gradle puts all artifacts in the dependency graph on the class path. So we need to tell Gradle to compile our artifacts on the module path. To do this, we ask that all code that was previously on the class path should be put on the module path, and the class path should become only an empty set of files. So let's copy this code snippet into our Gradle build script. And now let's try to execute again our code. And this time it worked, but we see here that the code has been executed on the class path and not on the module path. So it is executed as non-modular. This means that we need to also tell Gradle how to execute the code on the module path. So in this run block, we again need to say that everything that was previously on the class path should be put on the module path. We add our module to the list of modules to be resolved, and again the class path should become only an empty set of files. Let's also copy this piece of code into our Gradle build script. And now let's execute again our application, and we can see that this time it has been executed on the module path as desired. Now let's try to execute our tests. The tests were successful, but they have been executed on the class path and not on the model path. So again, we need to tell Gradle how to compile and to execute our tests on the module path. Here is a bit more complicated because both the test class and the class under test are in the same package. So we have a split package between the main module and the test module. To deal with this split package, we need to use the patch module option. So we ask that all code from the test source set should be merged into our main module. Additionally, we need to add JUnit to the list of modules to be resolved, and we ask that our module should read the JUnit module. So let's copy also this code snippet into our Gradle build script, but this is not enough. We told Gradle how to compile our test on the module path, but we also need to tell Gradle how to execute the test on the module path. And this is similar to what we did before, but additionally, we need to open our package to JUnit. We need to do this because JUnit uses reflection in order to analyze the test annotations in our test classes. So let's copy also this piece of code into our Gradle build script. And now if we execute again our tests, we see that they have been executed on the module path. Another thing you may want to do is to create a distribution of your application with start scripts. And you can do this in Gradle using the install this task. And now in the install directory, we will find start scripts for Unix-like system and for Windows. Let's execute this start script. Everything works fine, but the code has been executed on the class path and not on the module path. So again, we need to tell Gradle how to adjust our start scripts in order to execute the code on the module path. I will not go into details here because it's not important. The idea is that we need to adjust both the bash file for Unix-like systems and the bat file for Windows. So without further explanation, I will just copy this code into our Gradle build script. And now if we execute again install dist and we start our script, we see that this time the code has been executed on the module path. So let's recap. We needed to tell Gradle how to compile the code on the module path, how to execute it on the module path, how to compile the tests on the module path, and how to execute them on the module path. And finally, we needed to tell Gradle how to adjust our start scripts in order to execute the code on the module path. This is quite a lot of work. But as I told you before, we now have a plugin that does all these things for you, because 1 year ago, Paul Bakker and Sander Mack, which are the authors of the Java 9 modularity book, created this Gradle modules plugin, which provides full support for the Java module system. So using this plugin, you have nothing to do. You just apply the plugin and it does everything for you. And now that you saw how much work you have to do if you don't use the plugin, I think that you will really appreciate it. I also contributed to this plugin by adding support for the Kotlin and Groovy languages. So using it, you can also create modular applications in Kotlin or Groovy. Another use case I want to discuss is how to create a modular jar compatible with Java 8 or an earlier version. Let's suppose you have a library that is Java 8 compatible and you want to modularize it, but you still want that it works with Java 8. The problem here is that you cannot compile the module info Java in Java 8 compatibility mode. because Java 8 doesn't know about module info Java, doesn't know about the Java module system. So the solution is to first compile all sources except this module info Java using a value less than or equal 8 for the release option, and then you separately compile module info Java using a value greater than or equal 9 for the release option. And when doing this, you also need to include the location of the class files produced in the first step in the value passed to the ---- module path option. And finally, you combine all the classes produced in the first two steps into a single jar, which is a modular artifact compatible with Java 8 or an earlier version. You can do this with both Maven and Gradle. For Maven, the documentation shows you how to do this. You have also some example POM XMLs, so you just need to read the documentation and to adjust your POM XMLs accordingly. With Gradle is easier because the Gradle modules plugin, which we used before, also provides a method that allows you to do this. And calling this mixed Java release method with an argument specifying the target Java release will produce a modular jar which is compatible with Java 8 or with a target version specified as argument here. Another thing you may want to do is to create a custom runtime image for your modular application. And you can do this using the JLink tool, which has been introduced in Java 9. A custom runtime image is a distribution that contains only the modules required by your application. So it is smaller than a distribution containing all the JDK modules available in the standard edition platform. You can also create your own Java runtime environment with only the modules you need. But JLink has a strong limitation. It can only work with modularized artifact. And this is a big issue because most of the time your application will have some non-modular artifacts in its dependency graph. However, there are ways to solve this problem, and to see how to do it, we will try to create a custom runtime image for a small web application based on Vertex. This application should listen on the port 8080, and then it will serve a page saying hello and a name. And this name is taken from the name parameter of our URL, or if this parameter is not available, we will use nameless stranger as default value. In the main method, we just initiate our Vertex framework, and then we deploy the vertical we saw on the previous slide. The module info Java is also very simple. We only need to require the Vertex core module, and we export our main package. And this is the Gradle build script for this simple application. As you can see in the dependencies block, we only need to specify the Vertex core library. But this library has its own dependency, and the resulting dependency graph has about 20 artifacts. And none of these artifacts is modularized. So here's our problem: how to create a custom runtime image for this application that has lots of non-modular artifacts. And we'll see in a minute how to do it. But first, let's have a look at these lines here. Why do we need to configure these additional JVM arguments? Well, Vertex depends on the Netty library, and Netty common uses a class named sun-misc-unsafe. You probably heard of this class. It was designed to provide low-level mechanisms and to be used only by the core Java library and not by standard users. But because sun-misc-unsafe provides critical functionality that in previous Java versions was very difficult or even impossible to implement outside of the JDK, there are quite a few popular libraries that use this class, and Netty Common is one of them. The problem is that SunMiscanSafe is private API, and it has been removed from the standard platform in Java 11. Luckily, it is still available in a module named JDK.unsupported. So in order to make our application work, we need to add this JDK unsupported module to the list of modules to be resolved, and we ask that Netic Common should read this JDK unsupported module. Okay, now let's get back to our problem, how to create a custom runtime image for this application which has lots of non-modular artifacts. And the first option is to use the Modetect tool. Modetect can generate for each non-modularized artifact in your dependency graph a module descriptor, and it can add it to the artifact. So what Modetect does is to modularize each non-modularized artifact in your dependency graph. Modetect is basically a Maven tool, but I like Maven very much and I wanted to bring its functionality also to Gradle, so I wrote a plugin for Gradle that uses Modetect, which means that you can now use Modetect with both Maven and Gradle. And let's see how. With Maven, this is the POM XML for our web application, and here we use the Modetect Maven plugin. And then, for each non-modular artifact in our dependency graph, we need to configure its module descriptor. Most of the time, it's enough to provide a name for our module, and Modetect will infer what to put in the module descriptor, what the content of this module descriptor should be. This is possible because Modetect uses JDEPs. JDEPs is a tool introduced in Java 9 which analyzes the class dependencies, and it can also suggest the content of the module descriptor for us. And that's why most of the time we only need to provide a name for our non-modular artifacts. But in some cases, JDEPs may give us a wrong suggestion. And if this happens, we need to explicitly provide the content of our module descriptor, such as here or here. Modetect also allows us to configure the module descriptor using wildcards for the clauses in our module info Java. For example, here I ask that this module should export all its packages except those containing impa in their name. And here we needed to provide some additional services to be used by this module. With Gradle, we have something similar. We need to use the org Modetect Gradle plugin, and then again for each non-modular artifact in our dependency graph, we need to configure its module descriptor. And again, if the suggestions of JDEPs are not correct, we will need to provide the content of this module descriptor explicitly here. So Modetect is a very nice tool because it gives us a clean way to create a custom runtime image by modularizing each of our non-modular artifacts. And I used Modetect a lot. But once I had an application with a big dependency graph. It had more than 100 dependencies, artifacts in this dependency graph, and none of this dependency was modularized. And because I'm lazy and I didn't want to configure so many module descriptors in my build script, I asked myself if there is another way to do it. And I came up with an approach which I named it the BEDAS approach. The idea here is to combine all non-modular artifacts into a single one, into a so-called merge module. And then all we need to do is to modularize this merge module. And I also created a Gradle plugin that implements this approach. And using this plugin for our web application, after applying the plugin, we have the possibility in this JLink block to pass some additional options to JLink, and we can also tweak the content of our merged module. Most of the time this is not necessary because the plugin will infer what to put in the module descriptor of our merged module, but sometimes it may miss some information. For example, in the case of our Vertex application, it missed some services used by this application, and that's why we need to add them explicitly here. Okay, so let's see how it works, how we can create a custom runtime image for our application using this plugin. I will switch to the directory where we have this web application, and the plugin provides a task called JLink that will create this application with this custom runtime image. We also have a task called JLink zip, which creates a zip of our image. You can see here the zipped image has 32 megabytes. And here in this directory we have our exploded image. Let's see what's in this image. There are several directories here, and the most interesting are the bin and the lib directory. Let's see what they contain. In the lib directory, the most interesting thing is this big file called modules, which is 25 megabytes big. And this file contains all the classes required by our application. We can see what's in this file by using the JImage tool with the command list, and I will provide as argument the modules file. And now it prints all the classes in these modules. There are a lot. I will stop it and let's just grep for the module names. And you can see that this file contains only the Java modules required by our application. We don't have here all the Java modules available in the standard edition platform. And that's why this custom runtime image is smaller. Let's have a look at the bin directory. Here we see a lot of DLLs because I'm on Windows here. We also see here the Java executable and start scripts for our program. So let's try to just execute this program. And now if I open a new tab here and I say localhost 8080, it printed hello nameless strangers, and I can also provide a name, for example JCON, and then it says hello JCON. Okay, let's talk about another use case. Especially when you have an application with a graphical user interface, you may want to create a platform-specific installer for this application, and you can do this using the JPackage tool, available in Java 14. It was planned to be released in Java 13, but they postponed it. This JPackage is based on an older tool called Java Packager, which was available in Java FX, but it was removed in Java 11. And the Badass JLink plugin, which we saw before, also provides a task named JPackage that allows you to create such a platform-specific application installer. And to see how, let's consider a small JavaFX application that puts a label saying hello JCON on the screen. The module descriptor for this simple JavaFX application only requires the JavaFX controls module, and we also need to open our main package to JavaFX graphics. This is needed because the launch method here uses reflection in order to create an instance of the application class. And this is our Gradle build script. Here are two interesting things. First, we use this JavaFX plugin, which takes care of providing the right JavaFX libraries for our specific platform. And when using this plugin, you can put in the JavaFX block the list of JavaFX modules required by your application. Then we used again the JLink plugin, and it let us pass some additional options to the JPackage tool. For our simple JavaFX application here, we don't need to pass any additional options. So this block is unnecessary, we can throw it away and everything will work fine. I just put it here in order to show you how it is possible to do something like this. In this case, if we are on Windows, I ask that the installer should create a per user installation and that the user should be able to choose the installation directory. Okay, let's try to create such a platform-specific installer for our JavaFX application. I'll switch to the directory where I have this JavaFX application, and now everything I need to do is to execute the JPackage task. And now if I look into the JPackage directory, we will find here an installer for Windows because I'm here on Windows. Let's execute this installer. And now it will install my JavaFX application. Hopefully. Okay, and now if we look here, we see our HelloFX application, and if we start it, it says, as expected, hello JCON. The last thing I wanted to show is how to create a custom runtime image for a non-modular application. Sometimes you cannot modularize an application, or it is very difficult to do it, and you don't want to make this effort, but you still want to create a custom runtime image for this non-modular application. To do this, you need to create a custom JRE containing only the JDK modules required by your application, and then you need to copy all the classes and dependencies of your application along with the start script into the directory of this custom JRE. I also created a plugin that lets you do exactly this. And if we use again our web application based on a vertex, but if we don't modularize this application, so if we don't have a module descriptor or module info Java in our application, we can still create a runtime image for it using this plugin. And then we have this runtime block where we can pass additional options for the JLink tool, and we can also configure the list of modules to be included in our JRE. Most of the time it is not necessary to explicitly configure the list of modules because the plugin can detect by itself which modules are required. For our web application, we had the problem with the sun-misc-unsafe class, and we needed this JDK unsupported module. And this is a thing that the plugin is not able to detect, so that's why in this case we needed to explicitly configure the list of modules. Okay, we knew that we need to use this JDK unsupported module, but what about the other ones? How can I know that my application needs these modules? And the plugin let us know what it will use if we don't configure anything in this runtime block, and I will show in a moment, because it has a task called suggest modules. And when running this task, it will show what it will put by default in the JRE if we don't explicitly provide this list of modules. We see here the Java naming, Java compiler, and Java logging, and this is exactly what we need. And we put this and additionally the JDK unsupported module. Okay, we have a few minutes left, so I would like to show you how you can execute your custom runtime image in a Docker container. Okay. I have here a multi-stage Docker build. In the first stage, we create our custom runtime image. I have as base an image with Gradle 5.6 and JDK 12. We just copy the source files and the Gradle build scripts, and then we execute this JLink task. This will produce the custom runtime image. And then in the second stage of our Docker build, we used an Alpine-based image because it is much smaller. We copy the custom runtime image produced in the previous builder stage into a hello directory. We expose the 8080 port and we configure the start command. If we want to make our Docker image even smaller, we can take some additional steps and we can strip all the unneeded information from the libjvn using this strip command available in the bin-utils package. And I have created these images, so let's see them. Without using the strip command, the image has 69.4 megabytes, and with this strip command we have 65.2 megabytes. Okay, this is all I wanted to show you today. Here you see the link to the code and slides of this talk, and here are the tools and the plugins we discussed today. So thank you for your attention.